Hello everyone. So in this video we're going to be walking through the mechanisms found in practice worksheet 18 to give you an idea of some of the decision making that we decide to do and the answers to these, as well as hopefully provide a little bit more structure to doing mechanisms in the future. So let's start out with question number 1. And in this question we see that throughout the process of this mechanism, we start out where we have these two alcohols and we end up with a new ring after the reaction is done. And the formation of a ring should immediately let us know that this is an intramolecular substitution. Of course, there's a lot that goes into this that actually gets us to that point, but it's good to note what the actual reaction is going to be like. The other thing that we'll notice is that if we were to be numbering some atoms here, let's say we started out with this oxygen as number 1, and we look at 2, 3, 4, 5, 6, and let's name that other oxygen 7. In the product that's shown on the right-hand side, we see the same trend where this is clearly carbon 2, so we'll call this oxygen number 1. Here's 3, 4, 5, and 6. At some point, we are clearly going to be losing oxygen number 1 or 7, because this could be either one based on the numbering system that we've given. So let's go ahead and start looking at this reaction and think about the steps that actually get us to losing one of those. The first thing that we'll notice is that in the reagent side of things, we have H2SO4 and H2O. Of course, in a reaction, this forms H3O+. Needless to say, we have a strong acid in solution. And if we start out with something that's a strong acid, and we know that acid-base reactions are some of the fastest that we have, that means the first step is probably going to be that acting with a base. So, as per usual, we're going to redraw the starting materials just so that we have that good practice down, because we're then going to use these to draw out our next steps. So, this is the starting material, and we also know we have H3O+, that's going to be starting out in this reaction. Whenever we look at these reagents, we have to ask ourselves, well, clearly we see the acid. What is the basic site of the molecule that's shown on the left? Well, there's two possibilities. Both oxygens do have electrons, and of course that is really what you need to be a base. And when we look at those two oxygens and we're debating between them acting as a base, we can also state that either one is just as basic as the other, because they're both just oxygens and it's not like they're connected to anything different from one another. So now we need to think a little bit in the future, which is, what is the point of actually protonating one of these oxygens? Of course, it'll make it a better leaving group, and in the case of this intramolecular substitution, in an acidic environment, we would only have a weak nucleophile to work with. Neither of them will ever be a strong nucleophile. This means we must be going through an SN1 reaction, and in an SN1 reaction, we prefer to form a carbocation that is on a more stable carbon. Right, and so that more stable carbon would be one that has more substitution. In this situation, something like a secondary over a primary would be beneficial. And looking at our two alcohols, the one over here is on a primary, right? If I draw it up here, it might look a little bit better. The one down here is on a secondary carbon. So I would say in the first step of this reaction, it makes more sense for us to protonate the alcohol that's on the secondary carbon. This generates our next intermediate, which is the protonated alcohol, which is now OH2+. In this situation, since we've already decided we're probably going through an SN1 intramolecular substitution, the next step would be that our leaving group is going to leave. Because remember that in any SN1, the leaving group leaving is what gives us a place for our nucleophile to attack, because now we have our carbocation that is available. In this scenario, of course, our nucleophile is going to be this other alcohol. It can come in, it can attack that carbon. This forms that ring, because notice now, if we label these, this is 1, 2, 3, 4, 5, and 6. So we're forming a bond between the oxygen that we have labeled as 1 and the carbon that we had labeled as 6. But don't forget in this product that you do still have the hydrogen on that oxygen, which means that there's still a positive charge. So now to finish off this reaction, we just need to deprotonate that oxygen which we can do using the water that we kicked off earlier. So this will come in, grab that proton, kick the electrons over to that oxygen, and we form our product, which I won't redraw because it is shown up there as I've boxed it in blue. All right, let's do this second one. So for this second reaction, I just recognized that this actually is the incorrect product, so let me quickly fix that for us. There we are. That's the alkene that we want to form. In this scenario, we're sitting in a very similar spot where we see that we generate a 5-membered ring in the product, and we're losing some things and moving some bonds around from our starting material. Notice in this situation that the bonds that we see in our product must be between the things we have labeled as 1, 2, 3, 4, and 5 for this ring. Here's 1, 2, 3, 4, and 5. So at some point we need to form a bond between carbon number 1 and carbon number 5. In addition, we see that the alkene that originally started between carbon number 5 and what we will be calling carbon number 6, and here's carbon number 7 for us, has now moved to between carbon number 6 and carbon number 7. The movement of an alkene typically tells us that some resonance is probably occurring throughout this reaction. So we see we have some resonance, and we see an intramolecular substitution. With that in mind, and the fact that we once again have H2SO4 and H2O, I would say this intramolecular substitution is probably going to be an SN1. So let's go ahead and let's start off this reaction. Once again, we're going to redraw out those starting materials. Along with our H3O+, so that we can then utilize this. So now we have to ask ourselves, what is the most basic atom on this molecule? This is the same thing that we did above. Typically, in this case, we have two oxygens that can both act as the base. However, in this situation, it makes more sense for the one that's up top connected to this dash because it can form a tertiary carbocation that's resonance stabilized, while the other oxygen cannot. So that's what we're going to do. We're going to protonate this oxygen using the acidic H3O+. This then gives us a really good leaving group in the form of the positively charged oxygen that's now shown on that molecule. So with this good leaving group, it's going to leave because we know that we're going to be doing something along the lines of an SN1 for our intramolecular substitution. This new carbocation that's left here also assists us in the resonance step. Because remember that whenever we have carbocations can undergo resonance in order to be shifted to a different location on the molecule. This is necessary in this case because remember that forming 5-membered rings is much, much faster than forming something like a 7-membered ring, which would be what we would form if the alcohol were to attack now. So in this scenario, we would see this alkene would move in a resonance form that now gives us a secondary carbocation that is still resonance stabilized. Now notice this resonance isn't necessarily the most stabilizing thing, simply because we are moving from a tertiary to a secondary, but it is necessary to form that 5-membered ring. Because now we're in a position where our alcohol can nucleophilically attack that secondary carbocation, generating our 5-membered ring. Of course, this leaves us with an additional proton that we do need to deprotonate from that oxygen there, and we do have some water that we conveniently made earlier that we can just use to deprotonate that oxygen, giving us our final product. So both of these reactions are very similar in the fact that they both protonate an alcohol to make it a good leaving group, the alcohol leaves, and then a couple of small changes happen in order to reach a position where we can do a nucleophilic attack and form a new ring. Let's move on to one that is a little different from this, because this time we're no longer in something like acidic conditions. We have sodium hydroxide and THF in the example of this reaction here. The other thing that you'll notice is that we are once again forming a ring. So to no one's surprise, this is another intramolecular substitution. But in the case of having a strong base in solution, such as sodium hydroxide, this no longer makes me confident that it will be something like an SN1. Rather, this is more likely to be something like an SN2. So let's assume at the moment that this will be an intramolecular SN2. As a reminder, intramolecular SN2s rely on the fact that we have some type of nucleophile that's present in the molecule alongside the good leaving group. And we'll notice that if we do some numbering once again, call this oxygen number 1, that this would be 2, 3, 4, 5, and 6 is where our leaving group sits. And in our final molecule, this lines up very well with the fact that that oxygen could attack carbon number 6, kicking off the chlorine. So, in order for us to reach that final product, the most important part is that we need to make that alcohol a strong enough nucleophile to actually do the backside attack SN2 to remove our leaving group. So, in that case, we can start out here with our starting material redrawn, because now we have the OH bond that is necessary for us to show the acid-base chemistry here. So the alcohol is going to act as a base, the hydroxide is going to act as a base to deprotonate the alcohol, giving the electrons to that oxygen and giving it an overall negative charge. This has converted the alcohol into an anion, which is now a strong nucleophile. Since it's a strong nucleophile, that means it can come in, do a backside attack, and kick out the chlorine. This, of course, will generate our product, because that is the exact cyclization that we were going for. So whenever we're doing intramolecular SN2 reactions, typically it is a deprotonation followed by the backside attack and kicking out of a leaving group. Now we have another interesting reaction. This one is a bit trickier, and as we go through this set of reactions, these mechanisms, they will start to get a little bit trickier, especially when we get to the more complex ones. So notice in this scenario, we start out with a system of rings where we have these two rings that are connected at the same carbon. However, over here, we see that they are connected at two separate carbons. So it's going to be beneficial to us if we start out by doing some numbering to determine where everything is in the starting material and the product. I'm going to start out with the obvious number, which is going to be the one that's connected to this oxygen. There's no way to not know where this is in the product, because notice that this carbon is still connected to the oxygen in the product. Now I'm just going to take the 6-membered ring, and I'm going to go around and label it clockwise. So this is 2, 3, 4, 5, and 6. I'm going to do the same thing in the product, 2, 3, 4, 5, and 6. And this sheds a little bit of light on the situation. Notice that the carbons that I'm going to label with colors in this case, a green and an orange carbon, those are both connected to carbon number 4. If I keep the green carbon in the same place for the sake of being on the left-hand side here, the orange carbon actually moves in this case to be connected to carbon number 3. So in this reaction, we're actually going to have a rearrangement occur, where the rearrangement that we're talking about is moving the ring from a 5 to a 6-membered ring and breaking the C4 to the orange carbon's bond and form the C3 to the orange carbon. The question is, how do we do that? Well, this actually gives us some useful clues into how this reaction must work. Because in the case of a rearrangement, these are going to be seen in SN1 and E1. Because as a reminder, in the case of SN1s and E1s, this forms a carbocation. And only when we have the carbocation are we typically going to see a rearrangement occur. So that is the important place we need to get to having a carbocation. So let's start out by actually redrawing our starting materials for this reaction. There we go. Let's ask the question of, what is the first step going to be? Well, we get some clues from our reagents here. We have another scenario where H3O plus is being generated in solution. So this is a strong acid, which means it's going to react with a base that's present in our molecule. So the question is, what is the base in our molecule? In this scenario, it's actually impossible for it to be anything other than the oxygen that's shown up here. So this oxygen is going to act as a base. It's going to deprotonate the hydronium, and we are now going to have a positive charge on that oxygen. The good news is, now that we have the positive charge on this oxygen, it's very easy to see how we can actually form a carbocation. Notice that if we just draw a resonance form, taking the electrons from the carbon-oxygen double bond and utilizing them to now have a carbon-oxygen single bond, we end up with a carbocation that is now present on the original carbon that was connected to that oxygen. Now, if we want to form a bond between C3 and the orange carbon, which we can label down here, there's the orange carbon, here is C3, and break the bond between C4, of course that means that our carbocation is going to have to be on one of those two carbons. The good news is, in this scenario, we do have a resonance form that allows us to actually put the carbocation on carbon number 3. So there we are. We now have our carbocation that's present on carbon number 3, and we have carbon number 4 still connected to our orange carbon. So what we can do in this step is we can do the rearrangement. Because notice, by breaking this bond between carbon 4 and the orange carbon and forming a new one between carbon 3 and the orange carbon, we would have achieved our goal. How do we show this in terms of arrows? Well, we would show this rearrangement here, where the electrons from the C4 to orange carbon bond are used to form the new C3 orange carbon bond. When we do so, notice that we are actually going to have to now draw this with the new bonds shown. So here is the orange carbon, here is carbon 3, here is carbon 4. But notice that carbon 4 has just lost a bond, right? Carbon 3 actually has all the bonds that it needs because carbon 3 previously still had a carbon-hydrogen bond. Carbon 4 didn't have a hydrogen attached because up here it was connected to 4 other carbons. So by losing that bond, the positive charge to the carbocation that was originally on carbon number 3 can now be shown on carbon number 4. Now we're very close to the final product that we need to make, because notice the only difference between this intermediate and the end of our mechanism is that there happens to be an alkene between carbons 3 and 4. If we have carbon 3, which we can imagine is acting as a alpha carbon with an alpha proton and a carbocation on carbon number 4, we can utilize water as a base to perform an E1 reaction. So it can deprotonate the proton and form the alkene in order to give us our final product. So that one was a little bit more complex, but seeing the rearrangements and making sure that we're numbering things appropriately makes it a little bit easier. Let's take a look at another one of these that happens to do with now a basic condition, but still has some interesting ways of thinking about sort of rearrangements, but not really. So in this scenario, we're going to go ahead and we're going to do some numbering once again. Let's say that we have 1, 2, 3, 4, and 5 carbons here. Well, in the final product, we also have 5 carbons. The question just becomes, which 5 are the appropriate 5 carbons? Well, considering we start out with an epoxide here, we would say that it makes a lot of sense for the epoxide to be broken open during this reaction to make the larger ring that's shown in the product. Of course, this larger ring is made up of 4 different carbons, so which ones make the most sense to be those carbons? Well, it makes the most sense for the ones that I have labeled in red to be those 4 carbons, because there's no way for carbon 5 connecting to carbon 2. So in this scenario, we can actually label that to show this more appropriately. This would be 1, 2, 3, 4, which means that must be carbon number 5. So at the end of this reaction, carbon number 5 has a carbon-oxygen bond, and carbons number 1 and 4 are connected in between by an oxygen. Of course, in order for us to actually form this, since we have a primary alkyl chloride, this must be an intramolecular substitution that has to be an SN2. Now, whenever we're drawing this out, we need to think logically about what the first steps are and what makes the most sense to do. So, once again, we're going to redraw our starting materials. And we're going to think about what happens whenever they undergo this reaction. Of course, in this scenario, we have hydroxide, which is present and able to actually do the chemistry that we care about. So, if hydroxide reacts with this molecule, we actually have considered two leaving groups. We have a primary alkyl chloride, and we also have a primary epoxide. When we think about the rates of reactions of these, typically speaking, epoxides react much faster than chlorines, or than alkyl chlorides. So in this scenario, I would say that it makes a lot of sense for us to try to attack the epoxide first. And if this becomes a problem, we can come back and try something else. This, of course, will break open the epoxide in a basic epoxide ring opening, and that's going to give us a good nucleophile on carbon number 4. And notice that also on carbon number 5, we have now attached the alcohol group that we needed because the hydroxide substitution gives that to us. We also have our negatively charged oxygen from breaking open the epoxide ring. And this is exactly what we wanted, because in order for us to connect this to make the 5-membered ring, we needed this oxygen up here that I'm now highlighting in orange to be a good nucleophile and be attached to carbon number 1 or carbon number 4 and then substitute on the other. Of course, in this scenario, we are on carbon number 4 and we can substitute to kick off the leaving group that's on carbon number 1. And that's exactly what's going to happen. The oxygen will do a backside attack, kick out the chlorine, and that actually generates our product. So for this reaction, we have another scenario where it looks like we're doing a rearrangement. Because we start out with this oxygen, this alcohol, on what we'll call carbon number 1. We're going to label also carbons number 2, 3, and 4, because in our product we see if this is 1, this is 2, 3, and 4. So somehow our alcohol has moved from carbon number 1 to carbon number 4. This is clearly a rearrangement, which means that we're probably doing SN1 or E1 in this scenario. This is also supported by the fact that we once again have acidic conditions, so we have more H3O+. So let's go ahead and let's see what happens if we just start out by thinking about the same principles that we had previously when it comes to something like this alcohol acting as a leaving group after being protonated. So here's our H3O+ alongside our alcohol, which is going to act as the base in this scenario. It gets protonated by our hydronium, generating a good leaving group as this OH2+. And so that can leave on its own. This is what gives us a carbocation, which is available to actually do rearrangement. So now the question is, how do we do this rearrangement? Well, we still have to follow all the normal rules of a rearrangement in SN1 or E1. In this scenario, we actually have a secondary carbocation. However, the carbon that we labeled as carbon number 2 is actually tertiary. And any time that we are adjacent to a carbon that is more substituted, we can perform a hydride shift because remember that it's going to give us a more stable carbocation at the end of the rearrangement. So now we have a tertiary carbocation. In order to reach the product, we have to do something similar to a reaction that we did previously, where if we were to draw a resonance form here, we would see that we could actually end up with a secondary carbocation that is now reactive in the position that we want to install the alcohol. So in this situation, the H2O can act as the nucleophile to add into that position This, of course, gives us what looks like our final product, but it has an extra proton. So another molecule of water is going to need to come in, grab that proton, deprotonate that to give us our product. Okay, one more before we get to challenge mechanisms, and this one itself is actually a little bit challenging. So notice in this scenario, we have an epoxide, and if we look at our other reagents, we have a primary amine. The first thing that we need to know about this primary amine is that it in fact is a strong nucleophile. As a reminder, amines, despite not having negative charges, can still act as strong nucleophiles. So in this scenario, before doing anything else, it seems to make sense to actually utilize that strong nucleophile because looking at our starting material, we have really good electrophiles in the form of an epoxide as well as an alkyl bromide. So let's go ahead and let's redraw out that starting material and see how this would react with the given primary amine. Well, in this scenario, we would say that the primary amine is most likely going to attack the primary end of the epoxide. This is because this acts very similarly to a basic epoxide ring opening. This would then allow our electrons to be kicked over to this oxygen here, and that is going to give us a new bond between this carbon and this nitrogen. Now, showing this step off first is actually very beneficial, because it gives us an idea of how the rest of this reaction is going to occur. Because notice, this is actually starting to look already like the products. If we actually label the carbons up here, we would say this is 1, 2, 3, we'll count the nitrogen as 4, and this carbon is number 5. This is 1, 2, 3, nitrogen is number 4, this carbon's number 5. So we now have a pretty clear path in order to reach the end of this reaction. And that path includes the formation of an epoxide between carbons 1, 2, and the oxygen. Of course, we have on carbons 2, we have the strong nucleophilic oxygen, and we have the bromide leaving group on carbon number 1. So immediately, this is actually a possibility in terms of forming the epoxide ring. Since this is intramolecular, it should happen pretty quickly, so we're going to write this down as the first important step to reaching that product. Now there's only one thing left to do because that nitrogen currently holds a positive charge, and that's going to be to deprotonate it. That's what the triethylamine is actually here for, because triethylamine is just a decent base. And so it can come in, it can deprotonate that amine, and that actually gives us our final product. So for this reaction, what it involves is primarily just seeing that first step, because then from there, everything's able to fall into place much easier. The same cannot be said about the next reaction, which is our challenge mechanism and one of our 3. In this first challenge mechanism, we see that we're reacting this epoxide with HCl at reflux in order to do an interesting rearrangement. And that brings up our first important point, which is that this is undergoing a rearrangement, which means that this is going to be similar to an SN1/E1, importantly, the formation of a carbocation. So with that in mind, that gives us a little bit of information about how exactly this reaction is going to work. The other thing that we need information on is how does this reaction actually do the rearrangement? So what we're going to do is we're going to once again number some carbons to give us an idea. Here's 1, 2, 3, and 4. These are the 4 carbons that actually make up our final ring, with carbon number 1 staying connected to the 6-membered ring. Then we have carbon number 2, which must stay connected to the oxygen because carbon number 1 no longer does. We also have carbon number 3 and carbon number 4. So interestingly here, there's a lot that needs to happen for this reaction to actually work. One of the weirdest things is notice that carbons number 4 and 1 end up with a bond between them in the final product. So we need to form the 1,4 bond. In addition, we need to actually break the 2,4 bond, because notice that carbon 2 and carbon 4 are connected at the beginning. The last thing that we need to do is we actually need to form a bond between carbon number 2 and the oxygen, because it needs to have a double bond, but we also need to break the 1 oxygen bond. So let's look at exactly how this is going to happen. Well, in this situation, looking at our reactants, we have a strong acid. And anytime we have a strong acid, of course, acid-base chemistry tells us we're going to have to protonate something. In this scenario, we have to ask ourselves, what is the base in our starting material? In this scenario, the only possible base is the oxygen, so let's actually protonate that and see where it takes us. Now that we have the protonated oxygen, we can see that we're actually going to be able to perform one of our first important tasks in the form of breaking the 1 oxygen bond. Because remember, if we're doing a rearrangement, and we must have a carbocation when doing that rearrangement, that means it's going to be one of our first steps. So forming the carbocation here makes a lot of sense. Because when we form the carbocation in this location, we still have this somewhat hard to draw intermediate up here, but we have the alcohol with our carbocation, and so this is carbon 1, 2, 3, and 4. So we've done the first of our 3 important steps, breaking the 1 oxygen bond. Now we need to break the 2,4 bond and form the 1,4 bond. The good news is this can be done in a single step, because by drawing some arrows starting here and ending here, we can utilize the electrons from the 2,4 bond to make the 1,4 bond, which will break and form those 2 bonds concurrently. This, of course, gives us a square looking intermediate, where now, if we count out these carbons, this would be 1, this would be 2, this would be 3, and this would be 4. So we've made our 1,4, we've broken our 2,4. Notice that on carbon number 2, we should still have the alcohol. But now we have to keep in mind, where does the positive charge end up? Well, it's not on carbon number 1, because carbon number 1 has now a 4th bond. It's not on carbon number 4, because carbon number 4 up here had 2 hydrogens attached. It still has 2 hydrogens attached. It must be on carbon number 2, because carbon number 2 is actually losing a bond. There were no hydrogens on there, it was just 3 carbons and an oxygen, which means now that it's only 2 carbons and an oxygen, it is lacking an octet. So that's where our positive charge ends up. So from here, the electrons from our oxygen can perform resonance to give us a resonance form that shows the oxygen double bond to the carbon being formed. Now to make our final product, keep in mind the only thing that's missing here is that we just need to deprotonate that carbonyl. So in this scenario, we're going to utilize the chlorine anion that we have to deprotonate that and give us our final product. Challenge mechanism number 2 is somewhat similar, but this one requires a little bit more in order to actually form the final product. So let's go ahead and let's actually investigate where everything ends up in our final products. Well, if we were to number our carbons, we have 1 here, 2 here, 3, and 4. The reason I numbered carbon number 1 the way I did is because it's very easily identifiable over here as carbon number 1. And then carbon number 2 is also relatively obvious. It's the only one with the oxygen on that other side. And then 3 must be connected to 2, and 4 is right here. So this is another scenario where we are breaking the 2,4 bond, and we are forming the 1,4 bond. So this is another rearrangement. Which means that we must be forming a carbocation. So with that in mind, let's see exactly how that's going to be done. Well, in this scenario, after we draw out our starting materials, we can ask what happens with our reagents. It's another strong acid question. So we have our H3O+, and we're going to protonate a base. In this scenario, we have two options. We have the oxygen that's tied up in the ether, or we have the oxygen that is present on carbon number 1. At the moment, it makes more sense to actually use the carbon number 1, because keep in mind that typically whenever we're showing the formation of new bonds, we're typically showing those moving to the carbocation. Notice above, that's exactly what we did. To form the 1,4 bond, we had to have a carbocation on carbon number 1, and we were breaking the 2,4 bond. In this scenario, it's the same way. If we're forming the 1,4 bond, we need to have the carbocation on carbon number 1 instead of carbon number 2. So let's go ahead and let's draw that out. If we protonate that alcohol, we will end up with the OH2+ here as a good leaving group. This, of course, is going to then be able to leave. Upon leaving, we now have the carbocation that we desire. And this is a perfect time for us to actually form that 1,4 bond and break the 2,4 bond, because this is where we can do that rearrangement. Of course, by utilizing the bond electrons, we can break that bond while forming the new one. This is where we're now going to want to draw and number our carbons appropriately, because now we have this square here, where if this is 1, 2, 3, and 4, we can see that we've now formed the 1,4 bond, broken the 2,4 bond. Off of carbon number 2, we still should have this oxygen with the methyl group, and once again, we need to find out where that positive charge goes. Carbon number 4 started out with two hydrogens up here, and it still has the 2 hydrogens down there, along with 2 bonds to carbons, so it's clean. Carbon number 1 had 1 hydrogen, it still has 1 hydrogen, 3 bonds to carbons, so it's clean. Which means that it must be carbon number 2, which has now lost a bond, that is now going to have the carbocation. Now notice, unlike the last reaction, we actually cannot form the carbonyl directly from this reactant. Instead, we actually need to kick out the methanol at some point in order to actually make that carbonyl. So this is where the water is going to have to come back and add in, because we need another oxygen, and we need that oxygen to be able to form a double bond in order for us to actually use it. So we have this here. Now, the next thing that we need to do is we need to deprotonate the alcohol oxygen using some water in order to take away that positive charge. So now we have an alcohol and an ether on the same carbon. But this isn't where we're going to stop, because we do have some H3O+, which we can utilize as an acid to protonate the ether. This, of course, will set this ether up to actually leave the molecule. Now, when this ether leaves, it would generate a carbocation, and we could draw a resonance form to show the formation of the carbonyl, or we can just do that all in one step. So let me move this a little bit so that it's easier to see. So I can draw out this oxygen-carbon bond a little bit longer. So these electrons drop down as the leaving group leaves. And that gives us nearly the final product. The only difference here is that we just need to get rid of that proton, which we can do using more water or the methanol that we just kicked out if we would like. But that right there is what actually generates the product for this mechanism here. So that was a little bit longer of one. And now we're at the final challenge mechanism. So this challenge mechanism requires a little bit more information in order to understand. Because in this one, we're not utilizing a strong acid. Instead, we're utilizing BF3. And one thing that I'll remind you of is that BF3 is a form of boron. Boron exists as a molecule or an atom that lacks an octet because it's happy only having 6 electrons in its valence shell. And so it has an empty orbital, which makes it a really good Lewis acid, also known as an electrophile. The other thing that we see here is that in this reaction, we have another rearrangement. This time, we're forming 2 carbonyls, but the important part about the rearrangement is this must mean that we are forming a carbocation. So, in this scenario, let's redraw out that starting material so that we can see how it's going to react with our electrophilic boron. So, the question becomes, what carbons need to be connected here? Well, an easy way for us to actually determine this is going to be to number those carbons once again. So what I'm going to do is I'm actually going to start out by calling this carbon number 1. And we're going to say if this is 2, 3, 4, 5, 6, 7, 8, 9, and 10. What are we going to see happen? Well, clearly in this scenario, what we want to see happen is that this down here should be carbon number 1. Bear in mind that you could try to label this one up here as carbon number 1, but it doesn't make as much sense. Because if that were carbon number 1, we would have to see that that ring would get bigger, but as we'll see in the mechanism, it doesn't make much sense for that ring to get bigger, because then we'd have to account for how the epoxide oxygen plays into that. So instead I'm going to call this 1, 2, 3, 4, 5. We know that the epoxide is connected to either 5 or 6, so in the product, whenever we're asking the question of what is that carbon double bonded to an oxygen, that must be carbon number 6. This would be 7, 8, 9, and 10. So in this reaction, what we need to see happen is that carbon number 6 needs to stay bonded to carbon number 5, but now carbon number 10 needs to bond to carbon number 5. So we need to do a 10 to 5 bond formed. With that in mind, as we've seen before, in order for a bond to form between 2 things like this during a rearrangement, we want one of them to be a carbocation. So that brings up the question of how do we get a carbocation onto one of these? Well, it's not going to be carbon number 10, because carbon number 10 is currently just connected to a couple of hydrogens and other carbons. Instead, carbon number 5 makes the most sense, because notice that carbon number 5 would be one that's currently connected to the epoxide. And if we open up that epoxide and leave a carbocation, then it's very reasonable to put a carbocation in that location. So that's how we're going to start this mechanism. We're going to utilize the electrons from the oxygen of our epoxide, and we're going to attack the boron. This, of course, is going to give us an intermediate where the oxygen's going to have a positive charge, so it's going to be a really good leaving group, and that's going to be connected to the BF3, and the boron will actually have a negative charge here. Bear in mind that negative charge does not make the boron a good nucleophile, it's just that the boron now has that formal charge due to accepting more electrons than its valence shell normally holds. What we are going for here is that we do want to form that carbocation on carbon number 5. So we're going to draw the epoxide opening in order to put a carbocation in that location. This now gives us our oxygen with the BF3 still attached to it, and the BF3 still has a negative charge, but now we just have our carbocation in this position. From here, we're going to see that the rearrangement is now going to occur. The electrons from this bond can be utilized to form the new bond here. So this is where we have carbon number 5 connecting to carbon number 10, and this is breaking the 6-10 bond. So we end up now with our 6-membered ring that is connected to our 5-membered ring. The other thing that we can see is that what we had labeled as carbon number 6 should now have the positive charge. The question may be, why does that carbon end up having the positive charge? Well, that is simply because when we look at this, the carbon number 6 originally had 3 bonds to carbon, 1 to oxygen, and carbon number 10, and now it only has 2 bonds to carbon and 1 bond to oxygen. I also recognize that I drew this incorrectly based on the way that the ring is supposed to be, where essentially carbon number 6 has now been rotated around to be down here. Notice that this happens when that bond breaks, because the rotation can happen anytime between. So, now that we have this drawn appropriately and our carbocation is where it needs to be, the final step of this reaction can occur, because the bond between oxygen and the boron is very weak. Anytime we have something like boron, which is a Lewis acid, keep in mind that that negative charge, even though it has an octet, it's stable without having an octet in terms of not being too terrible. It's still a good Lewis acid, but it can exist in solution. So that bond must break so that we can form the oxygen-carbon double bond, giving us our BF3 back and forming our product. So that is how we do all of these mechanisms, and hopefully you learned something throughout the process.